So this is the second part on our chapter 2.3 regarding covalent solids, and we are now focusing on the hydrogen molecule in this lecture. So what we will do next is that we will solve the 2-electron Hamiltonian, and we will do that for the simplest possible case, so essentially a hydrogen molecule. And we will speak a little bit about electron spins subsequently and how that affects things for the states we have for the two-body electron system, and what kind of bonds we will then get subsequently out of our system. So we will learn that there will be so-called bonding states and anti-bonding states depending on the spins of our electrons in the 2-electron system we have solved, and then outline how more complicated systems could be solved with this approach. For example, the previous sp2 and sp3 hybridized orbitals, they could be solved in a similar way. But now, instead of solving a system for 2 electrons, we would need to solve the system for a little bit more complicated system. And of course, we would need to solve not a 2-electron system, but actually for 3 and 4 electrons to realize that we would actually have this kind of mode hybridization taking place. And then we will briefly mention that similar mathematics takes place also in magnetic materials. So we will see that there's a kind of like analog between the math, and why that's neat is that the magnetic domain formation and understanding that, like understanding magnetism on a kind of a nanoscale level and also on a macroscopic level, that's still a pretty high and active research topic in solid state physics. And there, well, we don't speak about Ising model here in our course much, but essentially, that's the kind of simplest model we could imagine that they would be forming magnetic domain structures. So the math that we will be outlining here, starts to look similar to the Ising model. So if you're interested, I recommend you Googling what's an Ising model and what's magnetic domain and what's magnetic domain formation. And you can spend an easy night reading about stuff in Wikipedia and elsewhere in the internet. But let's now get started. So what we want to do is that we want to understand now hydrogen molecule. And it's a prime example. It's a very good example to understand how covalent bonding takes place, because we're learning about mode hybridization here. And covalent bonds and bonding in general, it's very directional. And it arises from the fact that we have these very directional sp2 and sp3 hybridized electron states. And hydrogen molecule is a very, very classical example. And this can be connected also with the magnetism and magnetic ordering. So it's a neat system to study. And we start our mathematical formulation by just outlining the system we have. So we have 2 hydrogen atoms, and we place them at points capital A and B. So these are the locations of the nuclei, the atoms, and they have ground state wave functions. We assume that we have solved them already for individual hydrogen. And for an atom at point A, it's the phi A, and the atom in the point B, that's the phi B, respectively. And this is the figure showing the system that we're studying. So the bigger red spheres, these are the hydrogen nuclei, so a proton. And then we have the wave function, and then these blue smaller guys, those are the electrons. And please don't be fooled to think that I would consider electrons to have some kind of spatial structure. Of course, we know the best of our understanding is that the electrons are really point-like objects. So far we have not been able to distinguish any inner structure with electrons. So they seem to be point-like objects in that respect. Of course, there are wave functions, but nevertheless, there's no inner structure of electron. It's a fundamental particle. And then the distance between these 2 atoms, that's R. So the modulus of RB minus RA. So that's our system. We will now scrutinize and solve the Hamiltonian of this system. So we will form the Hamiltonian, and we will just write it. So we will have many terms. The first one gives the kinetic energy of our first electron. So h bar reduced Planck's constant, and nabla with the subindex of 1 is that this nabla squared operator operates only on the first electron and then 2 times the mass of an electron. So that gives the kinetic energy. Then we have the second term, and this gives me the kinetic energy associated with the second electron. So the subindex 2 denotes that we are now like describing the second electron. And then we have many other terms that give rise to the potential energy of our system. And of course, Hamiltonian is the creature, the operator that gives us the total energy of the system we're studying. And then of course, what we have here, we have the term E squared divided by 2 pi times the vacuum permittivity epsilon naught, so that the smart people already can tell that we're looking for the electrostatic potential energy of the electrons and the atoms and different contributions. So kind of like what kind of potential atom A causes for atom B, and what kind of potential atom A causes for the electron 1 and so forth. But more on this later. So we have many terms. We have 1 over R, so that this is the first term in the potential. Then we have another 1 over modulus of R1 minus R2. So the 1 subindex refers to the first electron, and then the 2 subindex, the label refers to the second electron. Then we also have other terms, so that these are then of a different sign. Please note the sign that we are now dealing with interactions, attractive forces between the objects of opposite charge. So here 1 over capital RA, so that was the position of the atom A, minus R1, so position of first electron. So that's a first attractive term. Then we have a second attractive term, so we have 1 over RB minus R2, so the attraction between the atom B and the electron 2. And then we have yet another term, so we have attraction between the atom IA and the electron 2. And then finally we have the attraction between the atom B and the attraction attraction between atom B and electron 1. And this completes the full Hamiltonian of the system. And what we see here is that we have many terms, and it's difficult to solve without approximations. Of course, with the computers we could solve that, but let's just do some physics along the way so that we can simplify things and neglect terms that don't really play much of a role here. So as I said, the first 2 terms are the kinetic energies of the electrons, and here the notation nabla I means that this operator nabla I only acts on the position vector Ri, so only on a given electron. And the first term inside the brackets, so the ones that are describing me the electrostatic potential, is that the first term there corresponds to the atom-atom repulsion, so the kind of separation between the atoms, 1 over R, capital R, and they are of the similar charge, so of course this is a repulsive force, so that we have a plus sign. And this, what it does, it basically only creates an energy offset, and this is something we can neglect because we are usually more interested in energy differences and not the absolute energy of our system. Okay, what we do next is that then we look at the second term inside the brackets, and this is electron-electron repulsion. So 1 over R1 minus R2. So what is the separation between the electrons, how far they are apart, and because they are of similar charge, it's a repulsive force. And this is also quite weak, and we will neglect that based on the fact that the electrons are probably quite far apart from each other. Maybe that's not always the case, but at least we can neglect that based on physical reasoning. We can also neglect the attractions between atom A and the electron 2, and similarly between the atom B and the electron 1. So we can kind of assume what this physically would mean is that the electron 1 mostly still resides with the atom A, where the electron originally came from, and vice versa. The electron 2, that originally resided with atom B still resides relatively close, and that kind of provides us the reasoning why these two attractions can be neglected. And now what we are left is that we are left with a two-particle wave function. So we can write that to be a phi and then two arguments inside. So it depends on R1 and R2. And what we do next is that we kind of assume that this is separable. So that we can describe that as a multiple of wave function A and in the position of R1, and then phi B in the position of R2, where these phi A and phi B are the one-particle wave functions. And we can now separately solve them. That's doable. And after that, we can form the two-particle wave function, phi. And before moving onwards, I will continue speaking a little bit about these multipartite wave functions, multiparticle wave functions. We see that the electron wave functions of these covalent solids or covalent molecules, they seem to be such quantum mechanical objects that that we need many electrons to describe their behavior and the bonding. But usually we resort to approximations, and we really neglect the fact that there are actually many body objects, many electron states. And instead we approximate things because it's far easier. A good example of this approximation that we implicitly do in the later chapters is that we will speak in future of a so-called band structure theory of a solid or solids. And this is, in fact, it will act as a cornerstone of our treatment to understand the electronic properties of solids, metals, and semiconductors. And this is really based on a single particle approximation. So this band structure theory of solids, and this is an example of a single particle electron wave functions in place. So we calculate a single particle electron wave functions out of a complicated solid state system, and then we just populate electrons into these states, and we pretty much neglect electron-electron interactions along the way. And this works quite nicely, but I must say here that this doesn't always work. So if you're interested in seeing, for example, cases where this single electron approximation fails, I really recommend you to look into Mott insulators. And another phenomena that is really based on two electron wave functions is superconductivity. So there, for example, we know, already from the structure of matter course and from the high school, that based on the BCS theory, is that it's the Cooper pairs, so two electron states that explain the low temperature superconductivity. So we really know that this is just an approximation, but a good physicist is perfectly happy and fine in using an approximation when it's enough. And we only resort to using more complicated models when it's not adequate, the simple model that we would prefer using. Okay, let's continue. So what we need to do next is that we need to comply with our solutions with the Pauli exclusion principle, so that the spins it must be taken into account. And this basically means that we will have antisymmetric wave functions out that would describe the total wave function. So this means that there's two possibilities, and the total wave function psi, it could be a case where we have spin up and spin down electrons, and this is a two-electron wave function, and this would be proportional then to a something like a superposition of two separable states. So the total antisymmetric wave function possibility for that will be that we have phi A times phi B, and because we want to have the antisymmetric wave function, we also need to have a case that we have phi A times phi B And same way, like we may have a psi total wave function for a case that the two electrons are pointing in the same direction, so that the spins of both electrons, they are up, and spins are now same. And then we would form a superposition state that would describe the spatial part of our wave function. And now we must have a minus sign in there, because we must ensure that the total wave function of the system is antisymmetric, because it's describing a two electron state. And this then means that the spatial part of the wave function may start looking different than the case where we have spins in opposite directions. So we will next verify very briefly that the psi with two arrows upwards, so spins up, is antisymmetric with respect to the particle exchange. And this is the property we must require from a fermion. So two spins upwards, and this is now the symmetric spin case. So if we exchange the two electrons, so we take electron 1 and put that then into the position of electron 2, and similarly we put the electron 2 into the position of electron 1. The spins are same, so that doesn't change the thing, the total wave function. So what must happen is that then the spatial part should be then antisymmetric. And this is the question that we should then solve. Like, is this antisymmetric? And we can do this by brute force calculation, so that we can check how this psi AB, the spatial part of the total wave function, how it looks like. And here we can exchange the electrons and the atoms, the positions, and then we are left with a case that we have R1 in phi B, and in phi A we have R2. Sorry about there's a typo. It should be a vector R2 and not this mess in here in the argument. And then we have the other term, so we have phi B R2 times phi A R1. And then when we can change the order, and we will have minus phi A times R1, phi A times phi B, minus phi A in position of R2 times phi B in the position of R1. So this is what we could do, which is basically like a change the order of our terms. So this guy corresponds to this and this, so that's what we do, and we take the minus out, and then this term here corresponds to this. So we just basically take the minus out, and now we see that what we have inside the parenthesis, this is actually a psi AB, so that this psi BA equals to minus psi AB. And this means that indeed the spatial part is antisymmetric in this case. So that's how we see that the electrons must actually have a certain kind of spatial arrangement in this case. So the spin part of the total wave function, psi, two arrows upwards, is symmetric, and the spatial part is antisymmetric. And the symmetric, and the total wave function is now antisymmetric. And basically, like what that ensures is that we indeed comply with the Pauli exclusion principle. And this is then like how the situation looks like schematically, so that we have the wave function of electron 1 denoted with the blue cloud, and the wave function of electron 2 is denoted with the red cloud, and in this case they may be of similar all these kind of like orientation or structure ordering. And psi, spin upwards and downwards, has a symmetric spatial part and antisymmetric spin part. So when we exchange the electrons, we see that the spin part is antisymmetric with respect to particle change. And this means that total spin of the system is 0, spin up plus spin down equals spin 0, and this is also called a singlet state. And what this means, that we have a total spin of 0, and this is why this state is also called a singlet state, is that if we would put this kind of state into an external magnetic field, a B field, the energy distribution of this state would not be splitting. So no fine structure would be visible in the measured energy spectrum. And because of this is called a singlet state. So it doesn't have any fine structure. But interestingly enough, when the total spin is not zero, we actually do start seeing a splitting of the energy structures when we place the system under an external magnetic field. So on the other hand, when we have psi 2 spins upwards, this has an antisymmetric spatial part and a symmetric spin part. And this means that the total spin is not zero, and subsequently this is called a triplet state. And this, why it's called triplet state, is that this state splits in terms of its energy eigenstates into further states when we place that into an external B field. So we speak that the energy structure has fine structure, and it splits. And because of that, it's also called a triplet state. And now, I have shown you these pictures, but let's try to elucidate why I'm showing them. So let me ask you next that how the symmetries of the wave function, how it affects bonding. So how a hydrogen molecule bonds are being formed. So what happens in the case that we have antisymmetric psi 2 spin upwards? So this means that the wave function vanishes when R1 is R2. Because in this case, the electron wave functions must vanish so that its symmetries remain as we require. And this means, because if the wave function vanishes and if the modulo square of the wave function tells that this is the probability of the electron to be there, if it vanishes, this means that we just don't have electrons there in between. And that means that the two electrons don't really overlap much. And because of this, we in fact have charge depletion between the atoms, and we will have Coulombic repulsion between the atoms. And if we have stronger Coulombic repulsion, this means that we actually have an anti-bonding state, and this is schematically shown in the figure here. So because of this kind of Pauli repulsion principle, we will not have electrons in between the hydrogen atoms much, and then this means that we will actually see more of a positive charge here and here, and because of that we will actually have repulsive forces, and this is a case of an anti-bonding state. And now we see the other case, so that if you have a symmetric psi, so one spin up, one spin down, the Pauli exclusion principle doesn't really restrict the electron overlap anymore. And what happens is that we may have charges between the atoms, and these provide Coulombic attraction, and the total energy of the system can be minimized by the atoms actually coming closer together. And subsequently, what we have is that we have a bonding state taking place. And that's shown in the figure here. So we actually can have electrons residing nearby, and this is indeed what happens. And because we have more of a negative charge here in the middle, these positive nuclei on both sides, they become attracted by this electron cloud, and that this is the process that pushes the two hydrogens closer together, and that's why we have a hydrogen molecule. So what we have learned is that even the simplest of possible calculations, they are not trivial, and we had to approximate things, and this is what we had to do already in the simplest imaginable scenario, these two-particle Hamiltonian for a hydrogen system. And if you would want to do a little bit more sophisticated calculations, we end up with quite lengthy calculations, and basically we should need to iteratively solve the problem at hand. And this is where we would start using principle of least action. So what we would want to find the smallest energy and the smallest action of our system. And then we would know that this is the most probable ending scenario. This is where the system will find its equilibrium position. So in practice, what we do is that we iteratively solve using a variational principle. So what we do is that we correct psi that we are seeking for. That should really minimize the energy E that is associated with the wave function psi. So this is based on the energy minimization principle. And this is when we kind of like are seeking and we iteratively are looking for the best approach. How do we find this minimum? So we start with some trial wave function, we calculate the associated energy states, and then we modify the function size slightly so that we get a smaller energy state, and then we start repeating a process until we find a close to optimal psi, the wave function, and subsequently the energy states. So we want to minimize the kind of functional, which we now in fact have. So it's not the psi that we are dealing with here. In essence, it's not a simple function anymore, but it's instead like it's a functional. So it's a function of functions, so that we're actually really changing the functional form of our wave function slightly, and that's the kind of mathematics, the branch of mathematics that we're doing here. So we're actually taking use of the calculus of variations to solve the system. It's neat that for once we're also taking use of the mathematics that we learn in university, and this is a good example of that. I like calculus variations. I mean, it's an elegant piece of mathematics, and it's nice to see that we're actually taking use of functionals also in physics. So it's not just a mathematical object that we are dealing in the courses. So what we have is that the energies that are associated with this psi, they are given by a form that we have psi, and this is like what we would be minimizing in practice. I want to show you here now. So we take use of the variational principle, so basically the principle of least action, and we calculate the energy, and that's the integral of a total wave functions and its complex conjugate times the Hamiltonian times the original wave function psi, and then we integrate this so that we calculate the total energy of the system, and then we normalize so that we divide this with the integral over psi star times psi, and then we integrate over R1 and R2. And this is way how do we calculate the energy, and once we have calculated that, we can try to minimize the energy. We change the functions slightly. What is the psi? We calculate the energy again, and then we repeat this process. Either by brute force, by Monte Carlo simulations, or by gradient descent, whatever you name it, by genetic algorithms or something smarter. And in the end of the day, we can optimize the psi and minimize the E, and that gives us the correct stable equilibrium position. And once we have solved our system, what we have is that we have now the psi, the wave function, and we can calculate the ground state energies, and roughly they are of the form that for the singlet state, so where the total spin was 0, the energy is of the form 2 times E naught plus a delta E spin up, spin down term. And then in addition, we have the energy of the triplet state, and it's of a similar form. So we have 2 times E plus a term arising from the spin up case. And basically the spin, 2 spins up, energy change is always positive. And this means that we do not have chemical bonding. And this has been highlighted here in the figure. So this red curve essentially tells me the energy change in the case that we have 2 spins upwards. And we don't have a case, we don't have a kind of like a valley here in this energy, and that doesn't then give me any bonding. But when the spins are differently, we have this bonding state, and this delta E spin up, spin down is negative valued, and it has a minimum close to the case where the interatomic distance A naught is unity, because we have normalized this value. And this is where we have the bonding state. So this is in the picture where we have the minimum of this term. So somewhere nearby here. And this is then that the total energy is being minimized, And that's the reason why we have this kind of potential curve for the energy. And finally, we're close to the end, I would just want to say that for large nuclei separations, the energy is of a form. This is the generic energy form that we have 2 times E naught plus some constant C plus minus X term, where these signs plus or minus in before the X term correspond to the singlet and triplet states. So that basically we can really simplify the equation that they are the same quantities, this delta E arrow up and down and delta E arrow upwards. And here the X is called an exchange energy term. And the nice thing about this is that this is exactly the kind of mathematics we're dealing with, like energy states that we're dealing with when we are speaking of magnetic ordering. So it's somehow nice to see that the same kind of behavior seems to be repeating again and again in different physical systems. So I will conclude that we have an energy states that are of this form, and this X term, this exchange energy here, is actually a spin-dependent energy term. Please remember this, spin-dependent, and this is particularly useful later when we will discuss magnetism and magnetic ordering, because we now see that depending are the nearby spins upwards or up and down, we may have a slightly different energy contribution. And if we then combine that with the fact that the energy of the system should be minimized, we start seeing that this actually might give rise to magnetic ordering of our system, how magnetic domains are being formed. They are formed because they minimize the system. So the total energy of the system depends on ordering of spins. If we have X, which is negative, then the opposite spins are favored. And this is the scenario that leads to anti-ferromagnetism as a physical phenomena. And if we have X larger than 0, then that means that the parallel spins case is favored, and then that gives rise to ferromagnetism. So these 2 different scenarios for magnetic ordering taking place on a macroscopic scale. And we now see that depending on the kind of microscopic forces that are playing their role between electrons, depending on how they are, we may give rise to a kind of macroscopic magnetic domain ordering, and specifically anti-ferromagnetic ordering may take place, or ferromagnetic ordering may take place. But more of that later, when we are encountering magnetism and we are looking into the first principles of that topic. So thank you for listening, and please follow up with me all the way down to metallic bonding that we will be discussing next. So thanks and bye-bye.